Hello everyone and welcome back to another problem solving video where today we're going to be solving IChO 53 which is about non-benzenoid aromaticity. So they're just aromatics but not benzenes. So we have this professor who researched about non-benzenoid aromaticity, and then we have a small cute little scheme right here where we asked to draw 2 and 6. So let's get into business. So a transformation from 1 to 2, we treat it with oxygen tetroxide and sodium periodate on an alkene. So of course that will form a ketone, right? So the first step will be a formation of the diol, right? It will just be a formation of the diol, dihydroxylation. And then after treatment with sodium periodate, that's going to cleave that bond, the diol, and turn it into a ketone like this. So 2 should be, let me draw on the answer sheet. So 2 should look like this, right? Based on the compound that was given to us. Okay, so that's 2. And then we treated 2 with some base. And then after that, we form an enolate, and we treat it with an acid to give 4, which is the same as 2, the connectivity, but the stereochemistry here is reversed, as you can see. This is a wedge, and this, that is a dash, and this is a wedge. So the stereochemistry has been reversed. And the same thing happens here is they treated 5 through the same steps to give you 6. Now you might be tempted to say that, oh, the same thing, right? The stereochemistry of this proton should invert. But we can't really say that for now, because we need to use a model to determine what the stereochemistry of 6 is. And as you can see right here, this ring is a fused ring, so there are 2 rings joined together, and it's also an alkene, and there's also a double bond right there. So the rings of the cyclohexanes will be fused together as so. And now let me draw. Now that's going to test my drawing skills. 1, 2, 3, 4, 5, 6. Yep, that's good. And another 1. 1, 2, 3, 4, 5, 6. Okay, that's good. Alright, so this is the model for from transformation from the enolate to 6. You might think it looks weird. Why isn't it a chair? It's because that we have a double bond on the bridge carbon. Can you really say it's a bridge carbon? I mean, it's fused, so yeah, I guess you could say it's a bridge carbon. So on the fused carbon atom that the 2 rings meet, there's a double bond right there. So it forces the geometry of the fused ring to be like this. And then we're going to add the substituents. So there's a methyl group right here. Okay, and there's also a methyl group right here pointing out, like so. Yeah. Okay, great. And then we have the enolate right here, and then O lithium. Okay, great. And then we have a proton source. And as you can see, this is our enolate. It's right here. So what's going to happen is that enolate always attack axially. So what it's going to do is it's going to go for an axial attack. So it should be either up or down. And in this case, our axial bond for this carbon is going down, because if for this carbon, this is axial down, this is equatorial up. So enolates always attack axially, so it's going to attack axial down, because that is where the bond, the axial bond provides us. It's going axially down, so it's going to act axial down position to give you 6, which is it's just the same thing as this, but we have the carbonyl instead. So I'm just going to copy from this one and turn these 2 wedges into two dashes into a wedge, to 2 wedges. Yeah, so it's mostly about the model of the fused ring. So there you go. Should attack axial down because this carbon bears an axial down bond. Okay, great. Let's continue. So now we have this is a big scheme. And they also gave us some clues, right? Yes. Okay, so ketone 4 is converting to ester 15. Molecular mass is 188. What's that for? Compound 8. Compound 8. Oh, they've already given us everything, right? On this scheme, so that we don't have to label anything else. Compounds, what else has been given? Compounds 9 and 10 has 5 stereocenters. 9 and 10 has 5 stereocenters and no carbon-carbon double bonds. So let me write that down. Okay, they haven't given us that. There are 5 stereocenters. 10, 5 stereocenters, and no carbon-carbon double bonds. Okay, great. It's been given. Assume that not heavy water. Assume that this water isotope is being used instead of the normal water of 13 or 14 from 11. Compounds 13 or 14 are 18. Oxygen 18 labeled isopomers, just a fancy way of saying isomers, but in an isotopic way. Ignoring isotopic labeling, 13 and 14 will give 15 with identical stereochemistry. Okay, great. So then we can also deduce that 13 and 14 must also have the same stereochemistry. And yeah, let's start. So from 4, we treat it with KHMDS, which is a base, and then A under THF as a solvent. So right here we have the formation of an enolate, right? And then what's happened here is that the enolate is being trapped by the triflate, the TF group, the triflate group. So let's see what the question asks us. It asks to choose the appropriate structure for A. So they must contain some kind of a triflate group, which 3 and 4 does. 2 also, all of them has a triflate group. Okay, don't worry about that. All right, let's see. So from the scheme, so the enolate must attack the something, right? Either 1, 2, 3, or 4, kicks out the leaving group depending on what we choose, and then grabbing the triflate group. So let me label the group that leaves. So the group that leaves will be this one, and then there. So now it's only a matter of the stability of the leaving group. So 1 and 2 is a very bad choice. It's a really bad choice for A, because its leaving group is quite unstable itself, so it's not going to leave. 3 and 4, well, 4 is quite a good leaving group because you have a triplet group, another triplet group which can help the nitrogen out, but 3 also has a phenyl group which can help the nitrogen out also. So I would go for 3. 4 is a good one, but 3 is better, so I would choose 3. So let me take that on my answer sheet. Where is it? Oh, A2, right? Choose. I'm just gonna say 3. Yeah. All right, let's continue. Draw the structures of 8 to 14 and clearly identify the stereochemistry where necessary. Also indicate the introduced oxygen 18 atoms for 13 and 14 as shown in the example below. Okay, so we need to mark an 18 above the oxygen. That's being labeled. So, okay, let's start from the scheme first. So 7, treated with another base, will give you 8. And that to me looks just like a normal E2 elimination, right? So here we have a base coming right over, grabs this proton, and kicks out the triplet group, which is a really good leaving group in itself. So 7 to 8. 8 should be an alkyne. So 8 should contain a triple bond. Let me draw the rings, the fancy rings, beautiful, beautiful rings. Who doesn't love rings? Beyonce loves rings, right? Single lady, single lady. Oh, is that copyrighted? I think my singing is too bad for that. I'm singing this with a ring on it. What am I yapping about? Alright, so that should be our 8, right? Yes, and let me indicate that too. That stereochemistry. Boom. Okay, great. Let's continue, and then we treat it with MCPBA, a peroxy acid under sodium bicarbonate. That's going to give us 9. So that seems to me like an epoxidation reaction. And they say that 9 has no carbon. 9 and 10 has no carbon double bond. So seems perfectly fine to me to say that they are. Oops, sorry about that. Hey, where's it? Oh my. All right. So it seems perfectly fine to me to say that it's a epoxide. It's an epoxide. And for 10 should be it's enantiomer. No, sorry, not enantiomer. It's diastereomer. So instead of wedges, we have dashes. Okay, great. And let's count the number of stereocenters. They've given us that there are 5 stereocenters. So let's count 1, 2, 3, 4, 5. Okay, that corresponds. This one, 1, 2, 3, 4, and 5. Okay, good. That also corresponds to what they have given us. And let's also check the double bond equivalence. So the double bond equivalence of this compound is 14 times 2, that's 28, plus 2, that's 30, minus 20, dB equals to 5. So let me check if this is correct. 1, 2, 3, 4, and 5. Okay, great. Everything matches. Let me see if they have specified anything about 9 and 10 for its stereochemistry. I don't think they have. Okay. So 9 and 10. Okay, great. Have they has 9 and 10? Okay, let's continue. So 9 after treatment with this silane under sodium iodide. Oh my god, my naming skills have just fell off so much. Okay, so what's going to happen here is that 9 right here has an alkyne, right? So what's going to happen right here is that your silane will be attacked by the iodide. So it will be attacked by an iodide. And then the SiC bond will return to the carbon, kicking out the bromide. It probably doesn't happen all in one step, but this is the intuitive way of seeing it. So you will get a carbene, a CF2 carbene. And then the carbene will add on to your double bond, forming the cyclopropene, which is really cursed. But is it aromatic? Not yet, because we don't have a planar carbon yet right here. This carbon is still not planar. Okay, right there. Let me fix my drawing a little bit. You know the reason that my videos are long, it's because I'm always fixing the drawing. I don't know, I just want my drawings to be nice, look nice, you know. And for 12, it's just the same thing, but we just invert the stereochemistry of the epoxide. So it's just going to be that. Great. So after treatment with 13 and 14, you will get something. And then after treatment with this, you will get 15. So for 13 and 14, they have 3 oxygens. So it means that it means 2 things. First is that this epoxide is broken, and sure it does, because we have water as our nucleophile, right? And the thing here is, it also tells us where the water will attack, because they say that 13 and 14, upon reacting with a base and methanol, will give you this stereochemistry. So it's telling me that the site of the attack of 13 and 14 are different, but it will yield the same product, meaning to say that 13 and 14 essentially has the same stereochemistry. So what's telling me right here is that there will be 2 oxygens here, and we must find an extra oxygen, and it's probably going to be right here. So we're going to focus on this moiety, which is derived from our cyclohexene that cyclopropene that we just made. And at first, when I was solving this problem, I thought that it was going to be a carboxylic acid, right? Normal carboxylic acid. But the thing is, there will be 4 oxygens, and that's kind of not really ideal, because it doesn't fit with the formula that they gave us. So if you see, if we connect the bond from this carbon to this carbon, that is just our cyclopropene that we just made, except that the fluorides that used to be here is now replaced by the carbonyl. So what's telling me is that the cyclopropene is attacked by the methanol, the protonated version of methanol, because we have a base right here. It's being attacked here. It's aromatic, yes. And then what's going to happen here is that OMe, negative charge, double bond. And what's going to happen here is that this bond will break, and this will grab a proton somewhere. Maybe from another molecule of ethanol, let's say. Like so, to give something similar to 15. So what's telling me here is that 13 and 14, the cyclopropene moiety right here, is being converted into a ketone. So then 13 with its double bond right here, which is wedge right here, this wedge instead matches with this wedge. So what's telling me is that the isotopic water attacks here. Why? Because if we attack here, we will keep the stereochemistry here, and we will invert the stereochemistry here. So from a wedge into a dash. So that's just going to tell me that this one right here should be oxygen, normal oxygen, and this one should be labeled oxygen, so oxygen 18. Nice. And yes, of course, the cyclopropenone in this case will be also labeled with heavy water, because not heavy water, water, oxygen 18 version, because when we use oxygen 18, we're using oxygen 18, so oxygen 18. Okay, great. And 14, it's the same thing, except that the isotope is not on that oxygen. It will be on this oxygen instead, for the same reason. And yeah, that's 13 and 14. Okay, great. Let's move on to part B. So compound 19 is synthesized as shown below in relation to non-benzenoid aromaticity. 19 can be used as an activator for alcohols, and 20 was converted to 22 via ion pair intermediate 21. So we know that 21 is an ion pair. So it has a positive and a negative. So it has a cation and an anion. So it's kind of a salt. Although the formation of 21 is observed by NMR, it gradually decomposes to give 18 and 22. Okay, great. So let's start. So from 16, we treat it with a bromine and acetic acid. That's just going to be the alpha halogenation. And so it can go both ways. So you can have bromines on the same carbon, or you can have either on each side, and they're both correct. So I'm just going to go with either on each side, because I think that is more observed, because, well, because that's something. I don't actually have an answer for that, but so yeah, they're both correct. And the benzene carbonyl, bromine, bromine. Okay, great. So that's our 17. It's also giving us that there are 2 bromines here. So yeah, that fits. So I took that and then put it in. So that's the clue. 18. Let's see what we do to get 18. We treat it with a base and then form 18. Okay, now let's see the double bond equivalents here. So that's just going to be 32 minus 10. That's 22, 11 double bond equivalences. Whoa, it's quite unsaturated. 32 minus 10, 22. Yeah, 11, yeah. Let's see, so how many double bond equivalences we have in 18? 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, so that's telling me that there must be a ring formation. And something kind of similar to Favorsky, I would assume. 5, 6, 7, 8, 9. Yeah, probably something similar to Favorsky. So let me see. Oh, wait. Oh, no, that's... Oh, sorry, it must be 18 here. Okay, 18 is right there. Let me see. Let me draw the simplified version. So first will be a formation of the enolate. And we have a bromine here, and the bromines are all eliminated, so that's quite convenient. So that's the first step, like so, and then the same thing happens to form another enolate, like so, and then this double bond moves here, kick out the bromine. Wait, let me try and draw that better. Double bond moves here, kick on the bromine to form. Oh, it's the non-benzenoid thing again. It's similar to this one that we just drew. So that's just going to be your cyclopropanone. They're really smart with this synthesis. And I'm just going to label it as phenyl groups then, because it's gonna get kind of messy. Oh wait, sorry, that's... There you go. Alright. Okay, so that's 18. Let's check the double bond equivalences if it matches 11. So the phenyl group has 4 equivalences. 8, 9, 10, 11. Okay, great, that matches everything. So, and then 18 treated with thionyl chloride will give 19. Still has the same double bond equivalences, but the oxygen is gone, replaced by the 2 chlorines. So it wouldn't be weird to say that the chlorines have replaced the carbonyl group, because they still have the same double bond equivalences. The oxygen just disappeared, turned into the 2 chlorines. Yeah, I think it wouldn't be too wild to say that. Okay, good. 19. Okay. Okay, great. Okay, now we have 19 and then only 21 left, which is an ion pair. Oh, they've given us some NMR clues, but okay. So 4. Oh, sorry about that. Okay, so 20 added with 19, and there is a loss of hydrochloric, the HCl, the hydrogen chloride, to form ion pair 21. So what's going to happen here is that, let me draw 19 first. Let me copy 19. So 19, wait, sorry, let me cut that. 19, 18, 18, 18, 18 is just this one. Oh, sorry, I am supposed to copy the thing. Boom. 19 and 18 right there. Oh, as you can see, we have a kind of like a transfer of the atoms. So we have the oxygen here, now it's on there, and we have chlorine here, and so it's switched places. So it is kind of similar to the step as mentioned here, right? From 11 to 13 is kind of similar, because as you can see, from 11 to 13, they also used water. They used water, and then the carbon bearing the two fluorines now is being converted into a carbonyl. But in this case, instead of water, they are using an alcohol, which is just a water replaced by an alkyl group. So I would bet that it would do the same thing, whereby instead of the CO double bond, now the O bears another alkyl group, something like that. So 21. So let me get 19 first. So 21 should just be, a carbonyl. Would be, okay. Wait. So it should just be a carbonyl bearing an alkyl group, which is just the group here. So that's 1, 2 carbons. 1, 2, and then a phenyl group with a positive charge on the oxygen. But since it is aromatic, I'm just going to put the positive charge on the carbon instead and replace that into a single bond. Okay, to give the idea of aromaticity. And then it says here that there is a loss of hydrogen chloride HCl. So it means that there must be one chloride left, and that chloride should be the counter ion. And there you go, that's 21, that's an ion pair, and oh, that's it for question number 7 of IChO 2021. This problem is probably the hardest one yet I have ever seen in an Olympiad exam. It's probably the hardest one. And yeah, if you like this video, like and subscribe. Thank you all. Bye bye.